Okay, we're starting on this problem. In case you just came in, we're working on this problem. It's my nice way of saying shut up.
This, the 6, is not starting amount of S3, delivery amount. So you're going to have to react to some amount here. It's going to have to react to that guy, which was entropy, because we want this to be 3.
Okay, so half the battle here is interpreting the question. Find the amount of NO2 that must be added to 1.3 molar. I didn't change that. I just did the math for you. 2.6 moles per 2 liters. That's 1.3 molar, okay? Has to be added to 1.3 molar of SO2. Okay, so they're saying there is some amount here. We don't know how much it is, but there's some amount that needs to get added to that 1.3 molar. We don't have any of this stuff yet, but we're gonna make it. When we make it, we want to have 0.6 molar SO3. So that means at equilibrium, we wanna have 0.6 molar. Okay, so the question, like turning the question into the ICE table, that's the point where we can do the X's, but this is kind of the basic part of the problem. Starting with 1.3 and some amount, and then we make 0.6 molar SO3. So let's just step through like our normal steps of an ICE table and see where it can get us. So the reaction has to go to products because there's no SO3 and NO as far as we know. It just says NO2 must be added to SO2. Okay, so there's nothing to start with of the products. So we have to be forming products, which means that the change has to be subtracted off of the reactants and added to the products. So at this point, you should see that there is a piece of information there that's very useful. 0 plus X is 0.6. So we actually know what the value is for the change, because these two are always a sum, right? So that means that this x is equal to 0.6, which means we're going to make 0.6 of SO3, we're going to make 0.6 of NO, we're going to use 0.6 of SO2, and we're going to use 0.6 of NO2. We don't know how much NO2 we started with, but we know how much we're going to end up using. If you wanted to do this like one step further before you kind of recognized that, I'm just gonna leave this as like initial concentration, okay? I don't wanna give it a letter because I think it'll just confuse it. So let's just say the initial concentration of NO minus X. We already know that this is 0.6 because that's what it tells us in the problem. And then this is X. So this is the point when you have to realize that you know what X is. Because you've got two unknowns, right? So we have to be able to either eliminate one of those or have some additional information somehow. So at this point, you have to recognize there's two unknowns. There must be a way for me to get one of those. And they're asking you to find the initial amount of NO2. So it's not that. That's like the answer. So X is equal to 0.6 here. So I'm just going to rewrite that equilibrium line using 0.6. So 1.3 minus 0.6 is 0.7. This one, we still can't get the initial concentration, but we know that the equilibrium, we're going to have to subtract 0.6 off of it. And then for both of these, the product is 0.6. Okay, so now this is solvable because we just have that one unknown. So K is equal to 3.2. Which is NO times SO3 over SO2 times NO. There's no coefficient, so it's like very just plugging in the values. I'll write it out symbolically just so there's not any confusion there. Okay, and then I'm going to plug in these equilibrium values. So 0.6 times 0.6 divided by 0.7 times the thing we're looking for. Don't, if you want to put in a letter, put like Y, don't put X. It's going to confuse you. Okay, the initial amount of NO2 minus 0.6. So now we can solve for that initial amount, which is what the question was asking. And the math on this one's pretty easy. So the math part was easy here, but and you can go ahead and do it. It's just, you know, some basic multiplication stuff. I guess you have to distribute one value. The math part is the easy part here. The hard part is interpreting what is the question asking, and then like recognizing that you know what that X is because they gave you an equilibrium amount. And to be honest, if they tell you an equilibrium amount, you know, you almost certainly know then what your change is, and you can apply that to all the other changes as well. Okay, so 3.2 times 0.7. Okay. Now, I'm not writing out every single little math step here to solve this out. I'm doing the 0.6 times 0.6 divided by 0.7, all is 1. So these three numbers, I'm doing that calculation there, and I get like 0.514. And then I'm going to divide that by 3.2 so that all of my numbers, I'm just isolating this term on the other side. It's okay if you're not following me. Go through all of the individual steps yourself. That's just fine. long as you end up with the same answer once you work through each individual step on your own, that's great. So let me just give everybody a second to catch up with that, and then I'm going to reiterate what the question was actually asking and what our answer means. So when we get this 0.76, that is telling us that if we mix 0.76 molar NO2 with 1.3 molar SO2, and we let them get to equilibrium, we will end up with 0.6 SO3. And that was the whole goal. It's like, how much do I need to mix in there in order to get 0.6 molar SO3? So just recognize that they're not always like just solving for some equilibrium amount. Sometimes there might be a little bit of working backwards. In fact, if they give you an equilibrium amount in the question, you know, like recognize, okay, there's some other piece that I'm looking for, not the actual equilibrium amount, but some other component. Yeah. So because you can multiply on the other side. So what I did, I took this term and multiplied both sides by that first so that I would get this. So I'm keeping it as an individual term. And I guess it would still be times 3.2 there. Now, 0.6, 0.6, and 0.7 on the other side. I'll leave them there. But once you just have numbers, you can go ahead and just do the math on that so that you get, stop, other way. Okay. 0.6 times 0.6 divided by 0.7. So this whole set of numbers is 0.514. So now it's much easier, instead of me distributing, because then I'm eventually going to have to isolate the variable again, and really it's almost already isolated by itself. So really all I just want to do is divide both sides by 3.2. So then I get NO2 initial minus 0.6 equals 0.161. And then I can just add 0.6. Now, if you got the same answer, it's totally fine. I just think it's a little bit less work to do it this way. You guys adore cross multiplication. Is this, let me look at it really a second. Yeah, it's sort of like that. I don't know. It's like you'd have to put a 1 here in order for that to make sense, but it's sort of like you're doing cross multiplication. So the only time you're you're going to have to distribute is if that unknown was the thing in the front. Yeah.
So it's 0.76 moles per liter.
Yes. Mm-hmm.
But since it's 2 liters, would you multiply by 2?
It says the amount. So if the amount was listed as moles, then yes, you would have to take this and say 2 liters times 0.671 molar per 1 liter and multiply it by 2. Yeah. So I guess it just depends on how the question, does it want to amount in moles or amount in molar? Or for that ridiculousness in grams or something stupid. I was going through like, I had a draft of the exam and I was like, I am making you guys do too many like mole to gram conversions. So I changed a bunch of those. There was one that was like atmospheres and torr. And I was like, come on, just change it to atmospheres. I don't need to have you guys wasting your time on that. So hopefully that doesn't make it easier. I guess there's less places for mistakes, but it also makes it faster is the main thing. Okay, so we need to talk about Le Chatelier's principle today, and then we will do this ice table problem, which is an incorporation of Le Chatelier's. So since we're here, maybe I'll just use this as a way to explain what we're talking about. So Le Chatelier's principle is always starting with a system that's already at equilibrium. Okay, so that's what you've got here. You've got this reaction, it's at equilibrium, and it even gives us the concentrations at equilibrium for all of these components. So we could go ahead and like calculate K because we know equilibrium values, so they don't give us K, but we could calculate that. I think it comes out to like 20 or 25, something like that. So it's pretty product favored. And then it says an additional pressure of 0.4 of Cl2 is added. So it's like we were at the balance point, so I know it's product high, so it's like we're right here, lots of products, not a ton of reactants, but then we add some reactants. So now we're not at the balance point anymore, right? We've messed up that equilibrium. Le Chatelier's principle tells us if we apply a stress, meaning like we mess up the equilibrium, the system's gonna go to re-achieve that equilibrium. Or it says like it's going to shift either products or reactants in order to, I'm trying to remember the wording, to relieve that stress, okay? So in this instance, we had our products and our reactants. We added some reactants. That's the stress. We need to relieve that stress, or a way to do that is like reduce the chlorine. We have too much chlorine, we gotta reduce that down. When you're talking about concentrations, it's really that ratio you're trying to maintain. So if I increase this, my ratio is all wrong now. So I need to balance it out so that ratio stays the same. Okay, so the way that I do that, if I've added some chlorine, okay, so I increased this amount, I've got to use that chlorine up. Okay, I have to get rid of it somehow. And this is not me now influencing the system. It's like I did this one little thing. Now how does the system respond? So that's me doing the thing in green. And then in orange, the system responds by reacting the Cl2 and the CO and making more CoCl2. So it shifts towards the products. That uses up some of that excess Cl2 that I put in there. Like that's how it's relieving the stress, is it's using that Cl2 to make CoCl2. The other way it's relieving the stress is like it was in equilibrium and then we messed it up, right? You can even think of this numerically. K, let's just actually do this. K was 20, I think. So the ratio should be 20:1. So I just messed up that ratio by increasing this, right? Maybe it's like 1.5 or something. So 20 over 1.5, now that's a ratio of 13:1. So a way that I fix that, if I increase the bottom number, how do I make it stay the same ratio? I have to increase the top number too, right? So mathematically, it's gonna shift towards the products so that this number can stay constant. So the top number gets bigger, the bottom number gets bigger. Now it's not perfectly like that because it's not gonna use up, it's gonna use up some of the bottom number too, but they're balancing themselves out. So if you see my hands, when I say we're at equilibrium, we add some more stuff, right? What happens is I use a little bit of that stuff up, but I also make some product in the process. So as the reaction shifts towards products, some of the reactants get used up, some of the products get made, and then I've re-achieved that ratio. Okay, so we will come back at the end and do this actual calculation, and we'll see how much did it change by. But let's just go through and like predict some of these more conceptually. Okay, so in this one, it's showing that you have this system at equilibrium. Okay, so it's got 1, 2, 3, 4 of the NO2s and 2 of the N2O4s. So roughly, I mean, we could solve out the K, but roughly it's a 4 to 2 ratio. Really, it's 4 squared to 2 because of that coefficient. But what happens if we throw more NO2 into that system? Well, now our ratio is off, right? We've got 1, 2, 3, 4, 5, 6, 7. Did I miscount those? 6? 1, 2, 3. No, there's 7. I must have miscounted them on that side, or maybe it added. Oh, it added 3 extras. That's why. So now it's a 7 to 2 ratio. Well, that's not the right ratio, right? It has too much of the NO2. So they react, and this guy forms an N2O4 molecule to fix that ratio back to what we know it's supposed to be. Okay, so a way that this is used frequently is to force reactions to go to products. So like, let's just pretend, I'm gonna change this to a gas so that I can use this for my example. Okay, let's pretend we have A and B and they're reacting in a solution, right? They're aqueous, okay? And we wanna make this gas, C. I don't care what it is. It's some gas we're trying to make and sell, all right? So let's pretend that the ratio is kind of low on the product side. So it's maybe slightly less than 1, but we're trying to get this stuff out. Like, it's not very efficient to have to put so much reactant in and only get a small amount of the product out. So what we do is we've got this liquid and the gas is being produced. We find a way to let the gas escape and like capture it into a container. So we're constantly removing some of this gas. So it achieves equilibrium. Then we remove some of the gas. Okay? The system knows that you've messed up its balance point, and so it goes towards the products to make more of the gas. So I remove the gas, that's the green thing. The system shifts to reform that gas. And in the process, you use a little bit of the A, a little bit of the B, they react and form some more of the C. So the green is the thing I'm doing. I take away some C. The reaction's stressed out. Oh no, we don't have enough C. It goes to relieve that stress. It makes more C. And so it shifts towards the product side. So I guess the one I just gave you is decreases C. So for the answers here, if I decrease C, the reaction's going to shift to replace that C. So most of these questions will be which direction, either left or right, or products or reactants, will the reaction shift in order to re-achieve equilibrium? That's probably the most common way that this is going to be asked. It could also say something like, you know, how does the final equilibrium concentration compare to where it was when it started? So that's like these arrows in red. So when I remove some C and the reaction re-stabilizes, some of A is going to be used up as well. So A would end up decreasing overall. Okay, take a minute, maybe 2, talk with your neighbors if you'd like, try to predict each of these others, just an arrow left or right, as to which way the reaction will shift in order to deal with that stress that we've placed on it, either by increasing something or decreasing something. Okay, so for the first one, green arrow, I increase the amount of A. The reaction's like, I've got too much A. What do I do with it? I get rid of it by shifting towards products, right? A and B react, they form some C. So that's the shift that the reaction does in order to reestablish equilibrium. Same thing with B. If I increase B, the reaction's going to shift to compensate. C is the opposite. If I increase C, I got to get rid of some of that, so I have to go backwards and form A and B. Got to use up some of that C. And then decreasing A and B, either one, is also going to shift it back towards the reactants. Again, because you have to like replace some of that stuff that you took away. Important note, remember that solids and liquids don't get included in the K expression. So they will have no effect in a situation like this. If you had like, I don't know, let's say B was a solid and you talked about decreasing B, it just wouldn't have an effect on the reaction. There would be no response. Because with solids, as long as we have enough to achieve equilibrium, changing the amount of them is not going to make a difference. Okay with this? All right, there's two other stresses that we talk about being put on a system. So go to this picture. Yeah. So this one isn't really directly related to K. It's more that the K has changed in different pressure situations. You don't need to worry about that. You just need to think about this and the next one, the heat, in terms of stress and how does the reaction react in order to compensate for that stress. Okay? So if you remember from chapter 6, ideal gas law. Oh, in fact, let's write this as pressure equals nRT over V. I'm just going to write it in that form. The things that can affect pressure in a system are the number of moles, the temperature, and the volume, okay? We're not talking about adding anything in because we only want to change one thing at a time. So we're not going to change the number of moles right now. and temperature is its own separate thing. So be aware that the primary way we change pressure in these systems is by changing the volume. So it might say the pressure is increased, or it might say the volume is decreased. Those are synonymous as far as we're concerned. All right, so we've got this system. So just look at this side for right now. We've got N2 plus H2 forming NH3, and we compress it. We drop the volume. That change in volume increases the pressure. It puts a stress on that system. It was balanced out the way it wanted to be. It was at equilibrium. It was balanced out how it wanted to be, and then we increased the pressure. When you have gases, they will actually respond by shifting to products or reactants that have less moles of gas to relieve that pressure. So it's not that we're changing the moles of gas, it actually changes the moles of gas in order to drop the pressure down, right? Because if I decrease the number of moles of gas, that would decrease the pressure as well. So on this side of the reaction, you have 2 moles of gas. On that side, you have 4. So if the volume is compressed, it increases the pressure, that's the stress, and so the reaction responds by going towards the side that has less moles of gas, because that will actually change the pressure back, or at least lower it from this increase that was caused. Because 2 moles of gas, remember, they're in this container, they're bouncing around, they're hitting the sides. 2 moles of gas is going to hit the sides of the container less frequently than 4 moles is. So it will actually reduce the pressure in that system by shifting it towards the one with fewer moles. This is only the moles of gas. If you had like aqueous in that reaction, or solids or liquids or whatever, you just wouldn't factor them in when you're counting up the number of moles, because it's only the number of moles of gas. If they happen to be the same, like if you had 2 moles of gas on one side and 2 moles on the other side, it can't do anything to fix the problem, so it doesn't change. But in this instance, if you increase the pressure, it's going to move toward the side with fewer particles of gas. And then on the other side, the opposite is true. If you decrease the pressure, it's going to move towards the side where there's more moles of gas. Again, you cause a stress. It's trying to reverse that. It's trying to relieve that stress. It's weird to think of a decrease in pressure as being a stress, but it's upsetting the balance, you can think of it as, okay? So how does it get that pressure back to where it thought it wanted to be? It shifts to where there's more moles so that it can experience that pressure that, you know, that was its optimum point before. You're basically figuring out how to reverse that stress to some degree. Okay, let's predict a couple of these. So one slide above. Okay, so take a minute or two and work through these ones. Okay, first two, it's a little bit of a trick question. It's a solid. There's no effect here. It's okay. Now you won't make that mistake again. Okay, so changing the amount of solid unless you get it to the point where you're like taking away so much that it's not saturated in that solid anymore. But we're not talking about that. We're just saying remove a little bit. It still doesn't have an effect because solids and liquids do not have an effect on that ratio. Okay, if we increase the pressure, it wants to figure out how do I decrease that pressure. So if I look at the moles of gas, this side has 4, this side has 1. And so it's going to shift towards the products so that it can bring that pressure back down a little bit. Because less moles equals less pressure. And then the reverse is also true. If I drop the pressure, it's going to go to where there's more moles to bring it back up. All right, we just need to talk about temperature now. Are we doing okay still? Okay. All right. Let's go to the picture again. So let's go to this one. Okay, so in this little flask, we have N2O4 and NO2 at equilibrium. NO2 is brown though. So I can tell you at that cold temperature, what does that say? -75, it's gotta be like liquid nitrogen or something. Okay, at that really cold temperature, it's very much reactant favored, okay? There's lots of the colorless one, very little of the brown one. As we heat it up, it actually changes the ratio that's desired for that temperature, and it shifts towards the products. Now, the way we explain this is by looking at, is the reaction endothermic or exothermic? Meaning, is heat required for this process to happen, or is it a product? Is it made? Okay, so they show you heat as a reactant here. The other way you would see this is a positive delta H, or just a label that says it's endothermic. Okay, all of those things mean that heat is required for this reaction to occur. So this one works just like the concentration ones. If I add heat, it's got to get rid of some of that heat. It needs to use it up a little bit. So it shifts it towards products. It uses up the heat, reacts it with N2O4, and forms NO2. We'll go back and do one that's exothermic. Okay, so in this one, negative delta H, which means heat is a product. It's given off when X and Y react. So if we increase the temperature, which is just adding heat to the system, so we increase the heat, it's going to shift that system to get rid of some of that heat. The heat and the Z will react and form X and Y. Okay, so it responds just like if you were to change concentration amounts. The biggest thing is you have to figure out, is it a product or is it a reactant? And then treat it the same as either of those. And then like this one, if it was decrease, it's going to go back to make some of that. And draw those arrows again. So if I drop the heat, it's like we're missing some heat, right? We want that heat, we're missing some of it, so it shifts to make more of the heat. Okay, So with the remaining few minutes, we probably won't get to solve this whole thing because unfortunately it is a quadratic equation. But I want to come back to this question just so you can see how we can like actually quantitatively do this. Oh, I don't actually want that. I don't know why I erased it. Okay, so I already solved K out for you, so that's good. K is 20. We can work with that now. And for my ice table, what are my steps? I set up the ice table. I determine which direction the reaction shifts. Well, guess what? If I didn't know about Le Chatelier's principle, I would have had to calculate Q, compare it to K, and say, okay, it's smaller, so the reaction has to shift to products in order for it to re-achieve that balance point. But I already know if I add some of the reactant, it's going to have to shift to products. So I don't need to calculate that. I just need to say it's going towards products. Okay, so what are my starting amounts? I didn't change CO or COCl2, but I added a pressure, a significant pressure comparatively to Cl2. So now that's 0.5. So it's no longer at equilibrium, but I know the direction it's going. So I know that the change is negative on this side and positive on that side because I'm making some COCl2. I really hope you guys aren't just memorizing like negative here, positive there, shift that way. Like, it's going to be a lot easier for you to keep it all straight if you think about it in terms, like picture the chemicals if you need to. C and O, Cl2 and Cl2. They're reacting, they're combining and forming a new molecule, right? That's why this side is positive, because they're making more of this stuff. So then the question says, find the pressure of CO when it returns to equilibrium. So that's this. So we can calculate X and subtract it from 0.3, and that will tell us what that new pressure is. So I'll go ahead and work through the math. I won't talk it out. I'll just write it out, but I'll try to write out like all the steps. And then if you want to work it out on your paper as well, there's only 5 minutes left, so we may or may not get to the end. So we'll just go ahead and with that, okay? Might have to erase some of this down here. So feel free to watch me as I do it if you don't feel super confident, or just go ahead and work the math on your own. What is that, 6? 2 times 3 and move the decimal 2 places? I think so. Oh, let's leave it until the end though. 20. So this comes up with, I have to keep erasing. I'm not about to like put 2 pages for every single problem, but apparently that's what I need. Delete, okay. So the x's here come out to be 0.67 and 0.18, because remember with a quadratic like this, you're gonna get 2 results. And you have to decide which one actually is valid, which one makes sense. So I cannot use 0.67 molar when I only have 0.3 molar, right? The equilibrium amount is 0.3 minus x. Well, I can't use up 0.6, that doesn't make any sense, okay? So it has to be 0.18. So the, oh, 0.12. Sorry. So the equilibrium amount of CO equilibrium is equal to 0.12 molar. I think that's what the question asked for, was equilibrium amount. Yep. Okay, you're not gonna have a quadratic on the exam, but you are gonna have them on the homework. Homework is due tomorrow night. I'm gonna try to spend more time on 14 reviewing, because that was like before spring break, because the exam's on Friday. So Wednesday's review day, and then the practice exams are due Thursday. So I would highly recommend that you do chapter 14 practice exam too, so that you can come in with questions, and then we'll spend a good amount of time reviewing that. Hey.
Hi. I won't be here on Wednesday because of softball, but then
Okay.
on Friday I will be here.
Okay. You want me to, I can record the review notes if that's helpful.
Okay.
Yep. Hi. What was that?
I'm just laughing because you're probably